great. Do you guys know why we shh to say quiet?
Babies.
Babies, exactly. I learned this after I had a baby. Somehow when the baby is upset, you just go shh, and it calms the baby. So somehow,
Because
I
it
think
mimes
that's why we say
what they hear when they're in
right.
utero.
They say it reminds them of their time in their mother's womb. Okay. Yeah. And so I don't know why I'm telling you this, but we had to take these classes on. I don't know. But anyway,
That's really cool. I never do that.
So to calm the baby, you can rock it, and that also reminds them of the time in their womb, or you swaddle them up so they're like all tight. That also reminds them of something. Well, anyway, if you ever become parents, you can do that. Yes. Well, I highly enjoy it. It's not for everyone, but I very much enjoy being a dad. So, all right, okay. Okay, but I've got to teach you correlation. So, just so we can assign values to this, okay? If you see something like this, what would you say the R correlation value would be for a plot like this? Okay, positive or negative? Positive. And strong, weak, what?
Strong.
Very strong. I would say if the dots are exactly on the line, I would say R is equal to +1. What about this?
Strong.
Positive or negative?
Positive.
And
Strong.
strong. R is also +1 here, okay? So R doesn't have much to do with how steep or shallow the line is. It's all about whether it's positive or negative, the direction, and how well you can predict, or how much scatter is there, okay? This one's a little bit of a trick question, but let's try this. Is R positive or negative?
Positive.
Okay, so in this case, I tried to make it flat. This is supposed to be flat. Okay? So it is neither positive nor negative. Okay? In this case, y does not increase or decrease when x changes. Okay? So the r here is 0. Okay? Because even though there's no scatter, y does not change, okay? And if you look back to what it means to be positive or negative, it says when one variable increases, the other increases, or when one variable decreases, the other decreases. Over here, when x increases or decreases, y doesn't change. So in this case, r is 0. Okay? What about something like this?
And what is the relationship? There's no relationship.
Yeah, so here there's no relationship. This is like the amount of money I have in my pocket and the length of my foot. Okay, is there a relationship? No, alright? Some days I might have a lot of money in my pocket. Most days I have not a lot of money in my pocket. The size of my foot, though, is going to be the same all of those days, okay? Unless something weird happens, but unless I become pregnant, and then my feet get bigger. Okay? That happens, just to let you know. So I was like, I need new shoes. It happens, okay. I believe you.
And R would equal -1.
Oh yeah, right. Of course. I'm distracted by my own stories that have nothing to do with the class. So R here, I would say what?
-1.
Okay, not -1 because there is a little bit of scatter. Okay, if there's no scatter, we would say -1. But here, I would say there's not a lot of scatter, so I would say negative maybe 0.9. Okay, maybe 0.9. Okay, what about this? Okay, positive, but there seems to be a lot of scatter, so we would say R is
0.5.
yeah, okay, 0.5. I mean, these are just ballpark estimates, okay? These are not exact values of R here, okay? I'm just kind of ballparking it. We would have R equal to what here? Yeah, something pretty close to 0, okay? 0, maybe off by just a tiny bit, okay? Something around 0, okay? So there seems to be no relationship between variables. All right, is this okay? All right, here's a tricky one. Okay, so yes, what you should say is this is nonlinear, okay? We have a nonlinear relationship, okay? And here's the thing though. R is only meaningful when we have a linear relationship. However, you can always calculate R, okay? So R is meaningful only for relationships, or for linear relationships, okay? However, R does exist for nonlinear relationships, okay? It's just, because it's just an equation, it's just a formula, so you can always throw numbers into a formula, and it's going to spit something back at you, okay? However, that number that it spits back at you might not be useful. So, in this case, we have a nonlinear relationship. You can throw the numbers at the formula, it will spit a number back, but it's not useful, okay? So I would just say R may be something like 0.7 here, okay? But this is not useful because it is not linear. So how can we tell if a relationship is linear or not?
Goes one direction. No?
Okay, maybe
Straight
my
line.
question, huh?
Straight line, no?
Yeah, okay, my question was too simple. It's basically you have to make a scatter plot, okay? You have to make a scatter plot, and then you decide, does a straight line work, okay? If sometimes you can just take a bunch of numbers and calculate the correlation for it, but you have to be aware that that it makes sense to use a straight line. Okay, so always check for linearity. To do this, make a scatter plot and look to see if a straight line makes sense. Sometimes for quizzes and homeworks though, or quizzes or tests or things like that, it's not practical to make a straight scatter plot, okay? Or even for homework problems, it's maybe not practical to make a scatter plot. So somewhere in the problem, it might say, check to see if somewhere in the problem it says, we made a scatter plot and it seems like a straight line is reasonable, okay? So or in the problem it might say, you know, a straight line reasonable or something along those lines. Okay. If there's nothing about that, if it just says, here's some number, here's a correlation coefficient, go, you might be doing something wrong because you might have a nonlinear relationship. Okay, and the stuff we're learning today only works for linear relationships.
So we had 4 points on that question, you wouldn't have us use time to make a...
Right, right. Because making a scatter plot, I mean, it's easy for me to just throw dots on a board, but making a real scatter plot actually takes time. So I'll either provide you a scatter plot, or I might say, we made a scatter plot and a linear relationship seemed reasonable, okay? Or, if I want to be tricky, I could give you a problem, purposely omit that line, and then you might have to say, wait a second, we don't know if this is linear, okay? Okay, now let's model the relationship. Okay, what does it mean to make a model? All right, what comes to mind when you think of model?
Draw or something?
Draw. Okay. Okay. So when I think of model, I think of there's like
Simulate.
supermodels, right? Fashion models. Okay. And what is a fashion model's purpose?
To show.
To show you what this dress or this outfit would look like on a person. Okay. Now it's a little bit crazy, but now it's like, what does this non-clothes look like? So a fashion model will show you what clothes might look like, okay? Or if you're a kid and you buy model airplanes or toy models, okay, it's supposed to be a representation of the real thing, okay? So you have a model airplane, you look at it, it's supposed to represent what a real airplane looks like, okay? When we look at modeling linear relationships here, okay, we're creating kind of like a small version or a small representation of what the real relationship looks like, okay? So maybe we want to model, you know, the distance you run and the calories you burn, okay? In reality, anytime somebody goes running, if two people run 1 mile, they're going to burn different amounts of calories, okay? With the model, it's going to say something like, if you run 2 miles, we predict you will burn this calories, okay? It doesn't factor in different people's heights and weights and different aspects of their thing, okay? But it just says, but according to the model, if you run this many miles, you should burn this many calories if you run, okay? It's just a very simplified version of life. You might model someone's, people's height and weight, and we will say, according to the model, someone who is this tall should weigh this much, okay? Somebody who's this tall, we expect weighs this much. Of course, everybody's different. Somebody who's this tall will maybe weighs more or less, okay? So the model is just kind of a simplified representation of the overall trend, okay? So if we look at the distance, maybe we look at the distance traveled and the amount of fuel consumed. For, I don't know, maybe a certain car, okay? So overall, the farther people drive, the more gas they consume, okay? So this is what the data is, all right? This person drove this far and used this much gas. This person drove this far, the same distance, okay? So if this is X's distance, this dot, you know, maybe this is like 60 miles, okay? This dot is over here, and this maybe is, I don't know, 2 gallons of gas, okay? Somebody drove 60 miles and used 2 gallons of gas. This person drove, how far did this person drive? Yeah, same amount. This person also drove 60 miles, but maybe burned 3 gallons of gas. Okay. What about this person? This stuff right here. So, I don't know, I'm just making up numbers, but maybe this person drove 40 miles and maybe burned 2 gallons of gas. Who knows? Something like that. Okay? Is that okay? I just highlighted 3 points in the scatter plot. Okay? So in your notes, it's important that these two should be aligned vertically and these two should be aligned horizontally. Okay? If you're going to pick out, if you're going to circle points, these two should be aligned vertically and they should be aligned horizontally. Okay? Because we're just making coordinate pairs. Is that okay? So when we look at the data point, we can say, you know, we see that somebody who drives 60 miles might burn as little as 2 gallons of gas, or might burn as many as 3 gallons of gas, or something like that, okay? When we make a model though, we're gonna just draw a straight line, okay? This line represents the model. And what the model says is, if somebody drives 60 miles, we expect them to burn 2.5 gallons of gas, or something like that, Okay? That's what this model says. Somebody drives, so the model says if you drive 60 miles, we expect you to burn 2.5 gallons of gas. Is that okay? And we just have to say, okay, well, this is the model. So if I drive 60 miles, I might burn more than that, I might burn less than that, but this is kind of gives me a ballpark idea of how much gas I'm going to use. Is that okay? And that's how this model works, okay? So we're going to create an equation for just this straight line, okay? And we just say, so this is the model. The model is just what we expect if we were to just kind of boil the relationship down to a single straight line. That's our model, and we just have to say, my model is not perfect. In real life, the true values could be higher than what my model predicts, or lower than what my model predicts. Okay, so when we make a line, okay, in algebra, do you guys remember what the equation for a straight line is? Yeah, everybody remembers these things, okay? Which is great. Equation for a straight line is y equals mx plus b. And what was m? M is the slope, and b is the y-intercept. Great. Okay. Well, the same elements appear when we make straight line models in statistics, but we change up the letters for you. Okay. Straight line, or what we call linear model. Linear, and we're going to call this linear regression model. Statistics. So what we are learning is called a linear regression model in statistics. And so here, rather than y, we put a little hat on it. This is literally called y hat. And we put the hat on it because the hat signifies a prediction, okay? Prediction or estimate of y. This is our prediction or estimate of y. Okay. And we bring the intercept to the front, and we rename it y-a, and then we put the slope over here and call it b. I apologize that we change up the letters and reuse the old letters in the wrong way. Not the wrong way, but just in a different way. And then when you look at a different book, they use different letters even still. Nobody can agree. Okay, so this is the intercept. And this is the slope. Yes, and if you take statistics again, I hope that doesn't happen. But, I mean, I hope it happens by choice, not because you didn't pass. A different textbook might use different letters. In algebra, we all say y equals mx plus b. In statistics, we use different things. Here, it's going to be y hat equals a plus bx. A is our intercept and B is our slope. Okay, and to calculate this, alright, a lot of smart people, they figure these things out, okay, involving calculus to minimize things. Anyway, we get to reap the rewards of their labor. And we just have a simple equation, a simple formula to get the slope and intercept. Okay, so first we learn the slope. The slope is b, and this is r s sub y over s sub x. And the intercept, I'm going to just write these equations down. Intercept A is equal to y bar minus b times x bar. So, bits of info you need. So to get your slope and intercept, there's 5 bits of info you need. You need R. What is R? Correlation. Okay. You need X bar. What's X bar?
Mean.
The mean. The mean. And what do you think Y bar is? So X bar is the mean of all of your X values. Y bar is the mean of all of your Y values. Okay? What is S? Standard deviation, okay? I'm going to put S sub x, this is standard deviation of all your X values. SY, standard deviation of all your Y values, okay? So you need the mean of X and mean of Y. And then you have the standard deviation of X and the standard deviation of Y. And it's just a matter of plugging these numbers into this thing and then using it to get your straight line equation. Alright. So let's try this out. Okay. Alright, so pretend like I rewrote R, X bar, Y bar, SX, XY, okay? So, because I'm going to give you values for this, alright? And then, this is, we're going to predict the miles driven for, that, and so let me do, X bar is equal to 30, Y bar equals 1.3, and R is equal to 0.8, S sub Y. Okay, so with these 5 numbers, use the formula for slope and intercept to create a linear regression model. Okay? So all you're going to do, it's just a matter of plugging in these numbers into this thing. You're going to get a value for B first, and then use that value for B using the other numbers to get A. And once you get that, throw that in. Replace the A and the B here. Okay? So go ahead and take a few minutes to do that. It shouldn't be too hard, unless you have no idea what I'm talking about. Okay, but yes.
You plug it into slope first,
Yes.
and then once you get B, you plug it into inverse.
Exactly. Okay.
Intercept.
So first you find your slope to get your value for B, and you're going to use this value for B to calculate A. Right? And so you're going to have a value for B and a value for A, and all you do is you just replace A and B in this thing right here. Go ahead and do that, and we'll try this out. And I made up these numbers so our model might not be super accurate, but we can work with it. I realize this number is probably not a good number, but that's okay. Alright, so I'm going to just throw up some answers. Okay, let's talk about this. Okay, so if you just plug in the value for r, s of y, and s of x, you should get 0.0248. Okay, did anyone not get that? Okay, all right. So now using this value 0.0248, and I actually left my value in the calculator, so I didn't do any rounding here. I know here I'm rounding to 4 decimals, but in my calculator, in my calculator, I typed in 1.3 minus, and I hit the answer key, times, because the answer key represents 0.0248, times 30, okay? And when I did that, I get 0.5552, right? So, or you can just do 1.3 minus 0.0248 times 30 if you don't have an answer button in your calculator. Okay. Is that okay? And I get 0.5552.
No.
No?
So
Basically, you just
Did I mess that up? I'll check. I will check.
It's at 6.
Yeah. Okay, this answer is correct. All right. Okay, so who's having issues with this though? What are you getting instead?
0.556.
Oh, that's the same. 0.556. That's just a rounding issue. Okay, not to worry. Okay, not to worry. Yes.
basically what you get, you just plug it into the E right there at the bottom.
Yes. Exactly. Okay. So on my calculator, I have an answer button. So I can just do 1.3 minus, and because this represents B, I hit the answer button, and it plugs in all this whole number, and I do times 30. Okay. It's a little trick you can do with your calculators to make your life easier. Okay. So I get this, and then so now that I have a value for A, and I have a value for B, I just put that in here. Okay, I got y hat equals A plus Vx, and now I have y hat equals 0.5552 plus 0.0248x. Is that okay? Alright, so my numbers, I just made these numbers up, so they weren't very good numbers, okay? But according to this is my linear regression model, okay? This Alright. We are trying to predict y based on x, okay? And according to our graph or whatever, what is our x? What are we using to predict y? What we are doing is we are saying based on how far we've driven, we want to predict how much gas we've used. Okay? So x is the distance I've traveled, and I'm making a prediction for the gas used. Okay? So another way I could write this, okay? I don't want you guys to get confused or lost here, so pay attention. All I'm going to do is say, instead of using x and y, I'm going to write down what they represent. So this is going to be gas used, and it's a prediction for how much gas I've used, so I'm putting a hat over it, is equal to 0.5552 plus 0.0248, and this is distance traveled. Okay, so this dot represents multiplication, right? Or maybe I'll put a small x. So it's 0.0248 times the distance traveled. So I'm using distance traveled to help predict the gas used. Okay. The book calls this the independent variable, and this the dependent variable. Okay, so make sure in your reading, as you do your homework, you can identify which variable we use to make a prediction and which variable we are predicting. Okay, we always use the x to predict the y. So we use x to predict y. And we have to be able to identify which is x, which is y. Alright, is this okay? Alright, so using this equation, tell me, if I traveled 40 miles, make a prediction for the gas I've used. If I traveled 40 miles, how make a prediction gas we used. Just plug in 40 as your distance traveled. Okay, do we know what to do, or are we totally lost?
That's good.
You plug it in for a Y.
Okay, so I've traveled 40 miles, right? So what is the variable that I do know? Do I know the gas I've used, or do I know the distance I've traveled?
Distance
Distance I've traveled, okay, and what was that distance I traveled?
40 miles.
40 miles. So all I'm going to do is I'm going to use this exact equation, and I'm going to plug in 40 right here, okay? So to get this, I'm going to say the gas used, our prediction for gas used is equal to 0.5552 plus 0.0248 times 40.
Now, where's the 40 from?
Where does the 40 come from? It comes from my question. If I
Oh,
traveled
okay.
40 miles, make a prediction for the gas we used. Alright? And then when we do that, we should get gas used. Our prediction for that is 1.5472. Thumbs up? Great. Okay, but this is a model, right? In reality, if somebody drives 40 miles, maybe they used way more than 1.5472, or maybe they've used less than 1.5472 gallons, okay? We call the difference between what actually happened and what our model predicts, we call that difference a residual, okay? So, because it's a model, we acknowledge that it's not going to predict things perfectly, okay? So the residual, alright, so I hear some talking, which is fine, it's just, if you have questions, ask the questions, okay? If I'm moving on to the next topic too early, just raise your hand and say, wait a second, explain something. So, are there any questions on this?
Can you just write up above this y hat 552 plus 248 x? It's y hat equals, it's the same as equals a plus b x.
Yeah.
That's just,
So y hat equals a plus b x, okay? And so my b is here, and my a is here, and I know I erased
you
it.
solved for b, which
We
is where you
solved
got
for
it,
b,
right.
and then we solved for a.
Yeah,
Okay, and then we plugged those values in to get this.
right.
Yeah. And that's okay with it. Alright, so we've got gas used. Is this? Okay, and so our model is not perfect. We acknowledge that there's going to be discrepancy between reality and what the model predicts. So a residual is equal to the difference between the actual value for y minus our predicted value for y. Okay? Or a residual, which we use the letter E, okay, is equal to y, the actual value for y, minus, and what's the predicted value for y? Y hat, okay? This is the difference between what actually happened and what we predicted would happen. So we predicted that this much gas would be used. Maybe the actual gas used was equal to 1.9 gallons. So what is my residual? Yeah, okay, so the residual is equal to 1.9, my actual gas minus what I predicted, 1.5472, and using a calculator I get 0.3528. Okay. Okay. Let you guys write that down. So, a residual can be positive or negative. If we have a positive residual, what does that mean? Does that mean the actual point or the predicted point was bigger? We have a positive residual. The actual point was bigger than the predicted. Actual value, positive residual means actual value was bigger than predicted value. And a negative residual, on the other hand, means just the opposite. You can say the actual value was smaller than the predicted value, or you could say the predicted value was bigger than the actual value. It doesn't matter, okay? Negative residual means. Okay, so let's look at, and this is important, okay? Sometimes when I throw equations and say this is how you get these numbers, we lose what we're trying to do, okay?
Yeah.
We make a linear regression model. Why? Why are we even bothering with this?
See the trends? No?
Huh? Yeah, it's we're making a simplified relationship, right? We're creating a straight line simplified relationship to explain the trend here, okay? And what we're trying to do is we're trying to say, okay, according to this model, if you give me a value for x, I can make a prediction for y. Okay? That's what the model says. If you give me, when we create a model, we say, if you give me an x, I can make a prediction for y. Okay? And we said for strong relationships, our predictions will be good. For weak relationships, our predictions will be bad. Okay? For a positive relationship, if you give me a big value for x, I expect a big value for y. For a negative relationship, if you give me a big value for x, we expect a small value for y, okay? Whether that's positive or negative, it doesn't matter, but negative is big value for x, small value for y. Is that okay, or am I speaking gibberish? We're okay. Okay. I want to go into the interpretations of these numbers, okay? We have, in our model, we say if we want to predict the gas used, it's going to equal this plus this times some value of x that we plug in, okay? So I want to talk about interpreting these values here. We've got the slope, and we have the intercept. All right. Can anyone tell me what the slope is? Okay, slope is b. Okay, and in our equation, the value for slope is 0.0248. Okay? So our slope, the slope is b, that's right, okay? And in our example, slope equals 0.0248. What is the definition of the slope? Or what does it mean to have a slope of 0.0248?
Isn't it the tail?
Okay, yeah, it's the angle of our line, okay? And somebody might say rise over run, but that's not a useful thing, okay? What we are looking at, okay? Our x variable, what is our x variable? The distance traveled, okay? And what this says, okay, if you can see it, is that if I bump up distance traveled, okay? So when we predicted, we said if I traveled 40 miles, the amount of gas I use is 1.5472 gallons, okay? What if I bump that up to, I traveled 41 miles? The amount of gas I used goes up by how much? By 0.0248 gallons, okay? That's how this works. If you increase your x by 1, we expect y, the y hat goes up by the amount of the slope. Can you guys see that? Okay. If we increase x by 1, y hat, our prediction for y, goes up by the amount of the slope. So, increase x by 1, our prediction for y which is y hat goes up by the slope. Okay, and if the slope is negative, it goes down by that much. So another interpretation for slope, okay, in the context of our problem is for every additional distance we travel, so every 1 more mile we travel, I expect the gas I've used to go up by 0.0248 gallons. So in context, for every additional mile traveled, I expect the gas used to increase by 0.0248 gallons. Is that okay? Alright, so let me talk about the intercept, and then I'll just put up a couple examples, and I want to make sure we understand this, because this is an important concept, alright? It's important that you can get to these numbers, okay? But statistics is all about relating this math concept stuff to real life, right? So, the intercept, on the other hand, is A, and our value for A is 0.552, or 5552, okay? The intercept is our prediction for y when x is 0. So in the context of our problem, and this is where I said, because I made up my numbers, the numbers aren't that great, okay? In the context of our problem, we're saying if we traveled 0 miles, I'm predicting I used 0.552 gallons of gas, okay? Now, in real life, if I traveled 0 miles, I would predict I used 0 gallons of gas, but because I made up some numbers, we ended up at this, alright? Okay, so in context of our problem, we're saying if I traveled 0 miles, meaning x equals 0, I predict our gas used is 0.5552 gallons, okay? And then here's a note. Sometimes it does not make sense to say x equals 0. And when that happens, then your intercept doesn't have a meaningful interpretation. Alright, is this okay?
What do you mean not meaningful?
Not meaningful. So, let's say we wanted to know, let's say we were going to predict someone's weight based on their height, okay? And so we might say someone's weight is 65 plus, I don't know, 10 times their height or something, okay? In that case, the intercept is 65. And that means we would predict someone with a height of 0 weighs 65 pounds. Now, it doesn't make sense to say x equals 0 if height is 0, because nobody can be 0 tall, okay? So that's why we would say it would not be meaningful in that case, okay? Okay, so let's say, alright, I don't know, let's say there's some animal.
But, so what do we do with it?
This looks like a duck. Okay, what's that?
What do we do with the intercept then? Like the slope, we could,
Then
we
you just, there's no, there's not a meaningful interpretation. This is the interpretation. It's your prediction for y when x equals 0. It's just, maybe it's not meaningful to have that. It's like saying, I don't know, we could create a model for fuel efficiency, okay, based on how much cargo you have in the car, okay? So if you have a lot of cargo, we expect your fuel efficiency to go down, right? We expect your gas mileage to be worse. And if you have no cargo, it expects to be higher, okay? In that case, it makes sense to have x equals 0, meaning you're not carrying any cargo. Okay? But in other situations, maybe we're trying to say, I don't know, how many, I don't know, I can't think of something, but, yeah, I can't think of something off the top of my head, but if you don't have a meaningful thing, it's just not meaningful, okay? And that's okay, all right? Just like the correlation R is only meaningful when it's linear, okay? If we have a nonlinear relationship, we still have R, and it still kind of gives us an idea of the strength and the direction, but it might not be meaningful, okay? So that's what we've got going on. Okay, so let's say we got some mystery animal that looks kind of like a boxy dog, okay? And we want to predict, you know, the weight of the dog based on its height, okay? So we're going to have A plus B times the height, okay? All right. So this is, you know, this is the same as y equals a plus bx, but we're just doing this, okay? We're going to run a couple minutes over. Okay. So let's say r is equal to 0.7, y bar equals 45, and I'm doing this out of order. X bar equals 26, and standard deviation of x equals 3, and standard deviation of y equals 7. Okay. Fill this out. Okay, figure out your A and your B. Okay, I'm going to just do this quickly because we're going to run out of time. And you can verify and make sure that you get the proper values for okay, so this is what we have. 2.533 plus 1.633, okay? You can, on your own, verify that these are the numbers we should get. Okay, so, okay. All right, what is the slope in our equation?
B.
Yeah, it's 1.633. And so here we are trying to predict the weight of this animal. Okay, we'll call this box dog. So a new species of animal called box dog. And we're trying to predict how much should a box dog weigh if we know the height, okay? And so the slope is saying, okay, you know, if we increase the height of the animal, okay? Let's say from 26 inches to 27 inches, how much do we predict the weight to go up? We predict the weight to increase by 1.633 pounds, okay? So the interpretation here is for every additional inch in height, we predict the weight to increase by 1.633 pounds, or whatever unit we're using, okay? important that we include we predict, okay? Because it's not that the weight actually goes up this, it's just our model, which is a representation of our predictions. The model says it should go up, right? But maybe I'll find a tall box dog and a short box dog, and it's possible that the tall box dog weighs less than the short one, okay? That's possible. The intercept is equal to 2.533, and the interpretation here, there's not a meaningful interpretation, but the interpretation is that if a box dog is 0 inches tall, okay, meaning x equals 0, we predict the weight to be 2.533 pounds. Okay? And you can't have a dog that's 0 inches tall. But if we did, that's what we would predict would be our weight. Okay? Alright. That's that. Please make sure you understand this model stuff. You're going to have a quiz in 2 weeks. Some of it will be on this stuff, and then some of it will be on the stuff we learned next week. So we'll see you guys next week. Enjoy your evening. Enjoy your week.